Hello dear students, in this session we'll see one numerical on design of two-way post tension concrete slab. Okay, uh, we required IS code that we have already used in the design of reinforced concrete structure, that is IS 456 2000, and also our post tension IS code, that is IS 1343 2012. So both IS codes are required to design the two-way slab. Okay, some part means what, some values we are going to use from IS 456, that's it. And if you remember, or if you recall, we have designed this two-way slab in x direction and y direction. So we have calculated movement, and for movement we have taken one alpha value, alpha x, alpha y, and this value depends upon the end conditions. It means four edges are uh, supported, or one edge is continuous, other end is discontinuous, and both ends continuous, like this. So that table we have to use, or that values we have to take from IS 456, and we have to check the designed steel or whatever we are going to design, that is spacing of cables or number of uh, anchors. So we have to check it for design, for flexure, shear, and for minimum stresses. Okay, so we have to go for the checks also, and we have to first we have to design this section, design the reinforcement, and then we'll go for the checks, and then we'll come to the conclusion, that is our design is okay or safe, or it is in the limit. Okay, so let's get started. Design of post tension two-way slab 6 meter by 9 meter with a discontinuous edge to support imposed load of 3 kN per meter cube. Cables of 4 wires of 5 mm diameter carrying effective prestressing force of 100 kN are available for use. Design the spacing at the cables in both directions. Assume FCK 14 Newton per mm square, FP 1600 Newton per mm square, EC 38 kilonewton per meter square. Now what we have to design this slab in both the directions, that is ly and lx. Okay, x and y direction, that's why it is called as two-way slab. Then we'll first collect the given data. Lx is 6 meter, ly is 9 meter. Just remember, everywhere whatever the dimensions I have given, one minute, whatever the dimensions have given, if it is 6 by 9 meter, it means what, 6 is the x dimension, and uh, y is the another dimension. So first dimension is always x into y. Okay, don't get confused, some students still doesn't know this meaning of dimensions. Okay, first one is lx, another one is ly. Okay, so lx ly is given 6 and 9. Imposed load is given 3 kN per meter square. The cables of 4 wires of 5 mm diameter are carrying a pre-stressing force of 100 kN. So force, pre-stressing force is given, and the wires carrying the pre-stressing force dimensions and number is also given, and these dimensions, the required dimensions, required properties, that is FCK, FP, EC are also given. Okay, then we first of all just remember we will calculate the loads, then we'll calculate the movement, and from that movement we'll calculate the height or thickness of the slab, and for that thickness of the slab we will design the reinforcement, and after designing of reinforcement we'll go for the checks. So this is the basic idea behind any type of designing. Okay, so just remember these steps very well, and just follow these steps. Okay, by common sense or by general way we will design. Okay, so there are less chances of missing any step or doing any mistake in the design. Okay, so just follow this general guidelines and then go for the design. Okay, so we calculate first load, assuming weight of prestressed concrete slab 24 kilonewton per meter cube. 24 is the density of concrete. Self weight of slab 0.12. 0.12 is what? 0.12 is given, just give me 1 minute. First of all, we will assume some depth, okay, some height or thickness of the slab as we do in the design of reinforced concrete slab. So here we'll assume the depth of slab as 120. So that's why we'll, by using that depth, we will calculate the self weight of slab, that is 0.12 into 24 is the density of concrete into 1 meter is the width of slab. We are going to assume for 1 width of slab per meter width of slab, and then we design all the things. Okay, so self weight of slab is calculated as 2.88 kilonewton per meter square. Then live load on slab is given, and it is 3 kilonewton per meter square. This value is given. Then we will assume floor finish as 0.12 kilonewton per meter square. You can, if you remember, you can at that time of exam you can assume, or this value is minimum. So if you remember to take the floor finish, then just definitely take this floor finish. Then total load is calculate or sum up all those loads, and we get the total load of 6 kilonewton per meter square. Then calculation of bending moment and spacing. Once we calculate the loads, then we'll go for the bending moment. And for this bending moment, we have to use that uh, alpha value, and we get that alpha value from IS 456 2000. Okay, uh, just for taking that Ly by Lx ratio, or now here what we are going to do, we are going to consider a middle strip, and then we'll calculate for the middle strip, end strip likewise. Okay, so Ly by Lx ratio, that is Ly is 9 and Lx is 6, is equals to 9 by 6 is equals to 1.5. So as the four edges are discontinuous from okay, four edges are discontinuous, this condition is given, discontinuous edge. Okay, here. Okay, from this we can say the four edges are discontinuous. Then we will check the value of alpha x and alpha y for Ly by Lx 5 meter and 4 edges discontinuous. Okay, we get the value of, or we can directly take the value of alpha x and alpha y from there. Then we'll calculate the movement in the middle strip in the x direction. So whatever is the load into 3 by 4th of Ly. Okay, this 3 by 4th of Ly value is 9, and 3 by 4th is for middle strip. Before that, how this 19.22 value has come, sorry, I just forgot that page, or I cannot find that page, the in between page, so I will explain here. Okay, so we'll take alpha x for calculation of mx. Alpha x is equals, mx is equals to alpha x into w lx square. Okay, w lx square. So alpha x value we'll take from the S code. W is what, 6 kilonewton per meter square, Lx 6 square. Okay, from there we calculate this mx, and similarly we'll calculate for my. Okay, that you know. Okay, and then we'll calculate the movement in middle strip. Middle strip we can take 3/4 of the middle strip. Okay, now this middle strip, now this is the cross section of the slab, and whatever this part is this is middle strip, and we are going to design for this middle strip. Okay, so middle strip, okay, the moment in middle strip mx is equals to 19.22, that moment we have calculated, into 3 by 4th of ly. For x direction we are taking calculating moment in x direction, that's why we'll take the span in the perpendicular direction, that is ly. Okay, and vice versa. Then using minimum cover of 30 mm for the tendons, distance between top kern and centroid of cables is equals to, now here we are expected to know the eccentricity. So for calculation of eccentricity, just this total is we have assumed as 120. Okay, we have taken in the load calculation that we are assuming the slab depth, thickness or depth of slab as 120. So this is half is 60, and just remember this 30 we have kept for the minimum cover. Okay, then whatever the value uh, 1 minute, and this 3 h by 6 is the value for the notation zone, core or core of the kernel. Okay, just remember that part, where we are keeping, we will keep, or we are not allowing any tension, we'll keep the tension minimum in this zone. Okay, so 120 minus 40, 120 minus 40 into 30, so we'll get the eccentricity E at 50 mm. Okay, from the bottom. Okay, then pre-stressing force required in x direction, m is equals to p into E. Now m is 130 into 10 raised to 3, this mx into p we are expected to find out, and E is 50. So p is equals to 2600 kilonewton. Then force in each cable is given 100 kilonewton. Then we'll calculate the spacing of the cable from this point, that is number of cables in x direction middle strip, force, total pre-stressing force divided by force in each cable, that is 2600 divided by 100 is 26. So number of 26 number of cables are there in the x direction, and we'll calculate the spacing between the two cables. Now middle strip we consider as 3/4 of ly divided by number of cables. So whatever is the distance we get, it is in mm, so that's why into 1000, and we'll get the 260 mm spacing. We'll round up to the minimum, that is adopting a spacing of 250 mm. Okay, it is very similar to the design of reinforced slab. Okay, uh, is it clear? Then similar way we'll calculate the movement in y direction, that is middle strip. So similarly we have calculated 12.1 movement by using that alpha coefficient alpha y. We get this movement, and providing a cover of 40 mm to cables in y direction, distance between cables and top kern is 120 minus 40 into 40. 40 is the cover that we have assumed. So here in y direction we get the eccentricity of 40 mm. So similar way we have calculated the spacing of cables in y direction. Okay, it is up to this part it is very easy, and it is similar that whatever we have done in x direction we have to do that same part in the y direction. Then cable profile is parabolic with the maximum eccentricity at center and concentric at the support. Step number 4, check for limit state of collapse. Now we have calculated the depth we have assumed particular depth, and for that depth we have designed for the spacing, and we have designed the number of cables. Okay, now we'll check that whatever we have designed. Okay, so first check is for limit state of collapse. Check for per meter span only. Ultimate moment in x direction 0.089 into 9 into 6 square. So it is 29 kilonewton meter. So ultimate moment, for this ultimate moment we will use the value mr is equals to that part. Mr is equals to we have taken that part from the. So AP is the area of pre-stressing cables. The number of cables in x direction per meter span is 1000 divided by 250, that is 4 number of cables for uh, limit state of collapse. AP is equals to 4 by 4. It means what we are doing, we are going to calculate the area of the reinforcement, okay, like this. And then EP is given, that is characteristic tensile strength of pre-stressing steel. It is given as 1600 Newton per mm square. Just refer IS code clause. Uh, we have seen the separate numericals on the each part, that is clause number 22.4.1 sections uncracked in flexure limit state of collapse in the IS code IS 1343. Okay, and from there we'll take these values and we have solved for it. Okay, AP is equals to AP into FU divided by BD into FCK. AP 314, FU, that is EP, it is 1600. B we are assuming for 1 meter width. D is the depth of slab. D total D we have assumed as 120, and small d by subtracting the cover. The cover is taken for the bottoms from is taken as 30 into FCK 40 is given. So we'll arrive this ratio from IS 1343 2012 to printing mistake 2012 appendix B for post tension slab. FU is equals to, just refer appendix B. FU is equals to we'll get this ratio of 1. Then from 11 from IS code we calculate the value, we can calculate the value of xu from the interpolation. We have done separate numerical on this part, limit state of collapse. Okay, so just go for it, and by interpolation we have calculated the value of xu. And from appendix B the moment ultimate moment capacity is calculated as FPU into AP D minus 0.42 XU. Okay, so FPU we know 1392. AP we have calculated area of uh, the tendons into D we take matlab 120 minus 30 90. Okay, and 0.42 XU 26.56. Okay, so we'll get the ultimate movement capacity, and it is higher than the calculated capacity. Okay, 29 kilonewton meter. So the ultimate movement capacity of the slab is higher than the minimum value required. Okay, that's why it is safe in limit state of collapse. Okay, then we'll go for the next check, that is check for deflection under service loads. That is check for deflection. The tendons are following a parabolic cable in x and y directions. Induced UDL acting upward, which are equivalent load in x direction. WC is equals to P into EX into Lx square. So that part we have done in the first unit. That means from P into E is the moment, okay, and W, what we do, moment is equals to W L x square by 8, okay. W is what, P is equals to WC, movement is taken as P into AX, okay. Like that we have calculated, or we will consider equivalent load in x direction. In x direction, per meter width, there are 4 cables and each cable carry 100 kilonewton. So 4 into 100, total force in 4 cables is 400 kilonewton. Ex E, we have calculated eccentricity, we have calculated here, just give me 1 minute. Just for your simplification, now here we will take the eccentricity, or will consider, just this is the cross section, and the total depth is 120, is 60, okay. And here we'll provide 30 mm for 30 mm for the cover. So this 60 minus 30 will get the 30. So this is the eccentricity located at this part, okay, that is 30 mm. So putting these values in this WCX, we get the 2.66 kilonewton meter value. Then similarly in y direction, for per meter span of per meter span, number of cables 1000 divided by 320 will get 3.12. 3.12 means what, 3 3 number of cables, okay. So from this 3.12 means what, here we have given as 4 cables carry, 4 cables are there and they are carrying a load of 100 kilonewton. So we have calculated exact value, that is 3.12 into 100 is the force, that is P is equals to 312 total force in 4 cables, or in 3.12 cables approximately, we are going to round up, is 312 kilonewton. Then similarly we have calculated this for y direction. In y direction we'll consider the cover as 40, okay. So similarly we have calculated WCY 0.616 kilonewton per meter. The deflection is given by alpha, it is there in IS code, IS 456. Q max is equals to alpha into Q Lx square upon D. Alpha is the coefficient 0.0772. This coefficient alpha is there in the IS code. Just go through it. You will get, or you can find all those values. Okay. Q is the UDL and this is unbalanced UDL. We'll calculate first the unbalanced load, and then we'll whatever is the unbalanced value, we will design for it, or we will check at least whatever we have done up to this part is safe or not. Okay. So Q is the unbalanced force. So how to calculate this unbalanced force? So total load we have calculated as 6, okay, and this is dead load and this is live load, okay. So this much amount is the 2.72 kilonewton per meter square is the unbalanced load. So we convert it into newton per mm square. Now we will calculate the Q max value. So whatever up to what limit we are going to uh, take that unbalanced load to the bearable limit. Okay, so do you remember this part? Okay, q max is equals to E into h cube divided by 12, 1 minus mu square. Mu is the Poisson's ratio for concrete. It's generally taken as 15.15, 0.15. E is 36 into 100 into 1000, and H 120 cube divided by 12, 1 minus 0.15 square. So we get this value of Q max. So we'll put this QLX, sorry, and we'll put this value in this equation. Q max is equals to alpha, that is alpha is the coefficient, into QLX divided by D. D is the flexural rigidity, 5.62. Sorry, we have calculated this part D. Okay, this is the D part. D is equals to EH cube divided by 12 to 1 minus mu square. Okay, this is the Q max value. But the maximum permissible long term deflection is 6000 divided by 250, that is 24 mm, and what we have calculated it is 4.80 mm. So our section is much more in the safer direction. Our section is much more in the safer direction. Then we'll go for check for stresses, that is per meter. Check for stresses means directly check for bending, whatever is the unbalanced load, and for that unbalanced load we will check. So we have unbalanced load of 2.70 kilonewton per meter. The moment due to this load in x direction is this is the coefficient W alpha into W into Lx square. Okay, so bending stresses developed are M by Z, but Z is B, what, that BD cube upon 12, like that. So Z is the section modulus for this given section. So stresses is equals to M by Z. It is 3.262 Newton per mm square, and direct stress due to pre-stressing is equals to P, sorry, F is equals to P by A. Then maximum stress in concrete at top of the slab, at top of the slab is 3.262 plus 3.33. Okay, so 6.95 is equal, or approximately 7 Newton per mm square. So the permissible stress in concrete at bending moment is that sigma CBC, if you remember, and it is for M40. It is there in the IS 456. Just check for M40. M40 FCK is 40 given. So M40, for that sigma CBC value is 13 Newton per mm square, and what we have calculated it as a 7 Newton per mm square. So it is also much more in a safer direction. Okay, so we have checked for the stresses, that is we have checked our given section for limit state of collapse, then for deflection under service loads, and check for stresses means unbalanced load. So maximum permissible compressive stress is limited to 13 Newton per mm square for M40 concrete slab. Okay, so we have uh, designed our section, and it is safe in all the three conditions. Okay, and this problem is much more lengthy. Okay, but it can be asked for 10 marks or for 12 marks in the final exam. But you don't have to worry about it, just refer the both the IS codes. And first part of the problem is the design part, and second part of the problem is the check or check cross checking for the various criteria, that is limit state of collapse, then service loads, and for stresses, unbalanced load. Okay, so just focus on the first part. First part totally is the calculation of movement mx and my both the directions, and from that movement we'll calculate the spacing of cable. Okay, so this is the first part. Then moving to the second part of the numerical, we have to check for limit state of collapse. For this limit state of collapse, we have to use that small table from the IS 1343 for calculation of XU value, and then for calculation of movement, we are going to use the appendix B for ultimate movement capacity. Okay. Then for deflection, we have used that alpha coefficient deflection value q max. Okay, this value. Give me 1 minute. Okay, from by using this q max is equals to alpha q lx square upon q l x raised to 4 upon d. Okay, d is the flexural rigidity. For this value also we have checked, and then we have checked for the stresses. What stress means here, we consider it as unbalanced load. Okay, for this unbalanced load we have calculated direct and bending stresses, m by z and p by a. Okay, for these values also we have checked. So this will complete our numerical, and it is easy. Just divide our numerical into two parts and just go for the checks. And it is very important, and in the exam it is compulsorily asked. Since it is one way slab is much more easier, we have to design there only the depth part also, and we doesn't go there for the checks. Okay, but here in the two way slab we have to design also, and we have to go for the checks. So just focus on both the types of slab, but distribute the numerical into 2-3 parts, and then just it will be easy to remember. Okay, thank you. If you have any doubts regarding this part, just feel free to ask, but uh, just revise the previous years that we have done there in the design of reinforced slab. We have designed the one way slab and two way slab. It is in the same parallel way. Okay, thank you.